constructability. This is something we've, with regards to coordination, we've been discussing. So, like between disciplines, so for motor sizes and things, but then also there's expansion joints in buildings. So being aware of those would be an example of constructability. I gave an example of constructability of even designing products that can be purchased, like that 1200 kVA UPS that maybe you can't have a 4-wire output, just depending. What we usually do is 3 or 4 the predominant manufacturers. We just get their worst case dimensions, and that's how you decide how big of a switchboard to put on the floor plan. And that way, when it's competitively bid, if that's the case, that's why you would be doing that. You're sure that all of the manufacturers will fit. And usually, I mean, they're reasonably within the same sizes, but electrical rooms, and we'll have a look at that here in a short time, is those, they're premium, the buildings are built for people rather than for mechanical and electrical spaces. We really have to fight for the space though. So the worst case dimension can be a plus and a minus there. Overhead and underground routing is another constructability thing. I gave an example last night about if you maybe had a CT cabinet on one side of a wall and your switchboard on the other, and there's a 3,000 amp service, that like you just think about the conduit bins that have to happen to do that. Like physically, the contractor wants to know what you had in mind when you decided to do this, because it's not going to work. We need to update the floor plan or something. So do your best to help the team think about what's really happening out there. All right, I'll keep that short on that subject there. Any questions on constructability topics? Okay, great, we'll keep going. Basics of electricity and safety. So there's electrical engineering degree paths, but there's also architectural ARC-E engineering degree paths. Both great for consulting engineering paths. The electrical engineering path tends to have more of the basics of electricity involved. So I just want to note here briefly, very briefly, about AC power, and then that being an alternating waveform, and then DC, and going back and forth as well, positive, negative, and back and forth, and then DC being not going back and forth and not alternating negative, positive, just staying constant. It is by the process of creating a potential. So for instance, if you had a permanent magnet motor generator and you had put fuel in it, maybe diesel or natural gas fuel, and it starts turning, that motion induces an electric field, electromagnetic field, and causes, should load be there, that voltage potential creates the opportunity for electrons to move. And when electrons move, they can do work. They also create heat, right? So it needs to be big enough wire for the amount of work that you're pulling, demanding. There's, to change speeds of motors, like for a typical household fan, there's multiple coils in there. You're physically going to a higher or lower voltage, and that's why it spins faster or slower. Commercially or otherwise, in the HVAC and the motors that we use in buildings, other than in residential, usually they might have a contact starter or a combination starter. So we're saying, you know, plates coming together to turn off and on. Could also be an electronic, so like a variable frequency drive, such that it is changing from AC to DC, and then on the output, recreating by pulse width modulated signals the sine wave to kind of make it look like a sine wave enough to then you then control the speed by varying the frequency, and the frequency being how fast, 60 hertz. So how many times per second is it alternating? Load flow would be as such like, and we described for the panel schedules quite a bit already, I think. So I'm going to note just other than that they accumulate up to the service. So you plug something into a panel board, then that panel board gets plugged into a distribution panel, and that distribution panel gets plugged into our motor control center, and all of the loads and the demand factors stack, which is the electrical code. Chapter 2 really goes through that. Heat loss. So as I said, up here, the electrons are moving, and especially if you're going to do a lot of work, and there's a lot of them moving, they create heat in the equipment, and also physically if they're turning motors or otherwise. So electrical rooms, even if there are no moving parts, the electronics and the bus bars, those are all heating up, and they're letting off heat into the room. And for that sake, so for instance, the code requires for dry type transformers, although the insulation levels are high enough, and usually it doesn't require it technically, but might require the room to be fire rated, maybe a 1 hour rating. If you get over 35,000 volts and you need a transformer volt, that's a whole nother situation of like a 3 hour rating. If it's an emergency room, you might also have those concepts, but we're getting into the fire rating of the room when I was discussing the heating. So the heat loss needs to be removed and or exhausted. And if it is active electronics, such as a UPS system, they might be giving off a lot of heat. And so it's coordinating with your HVAC mechanical discipline counterparts to make sure those rooms have adequate or equivalent for the heat loss. So the heat loss calculations usually involve that concept, usually something such as consulting guides that have published information to gauge what likely, based on the load, depending on the type of equipment, there would be. So we would maybe give it in watts. So like a panel board might be 42, whole panel board might be give off like 200 or 400 watts of heat. And I mean, the heat loss conversation is the watt loss, heat loss, heat gain. If you're the HVAC engineer, you might consider this heat gain because there's heat gaining in that room, and I need to, but just try and put them in perspective. Don't blindly do the calculation and then hand it over. So I said 200 watts or so for a panel board. If you can imagine, if you had a thermographer, like a red infrared imaging gun, and you were pointing it at a panel board that had all the circuits and all of them were turned on and all of them were doing load. So the human body, about 100-watt light bulb kind of is on average. So you think about how much the human, even just the sensibility of how you'd feel. We're not even talking about very much heat. So just be sensible about these kinds of calculations, and the tons of cooling that could happen can be a lot if it's not completely understood, and or it can be understood. For instance, in the technology rooms, IDF and MDF rooms, those rooms can be undercooled. So voltage drop, I'm not going to go through it too much here. There's a nice article on Nebulous here, that LLC's website, that has pretty good and very specific and a couple different ways to do it as well. So voltage drop being that the further you go away, or the further the load is from the source, the wire itself is also a load. So as you demand current, it's going to reduce the amount of voltage that will get to the source, to the equipment, and that might not allow that equipment to operate very well, and it might have issues, or otherwise it's wasting energy because now you're just heating up the kit. So the way to solve this is to have larger wire. You can have two larger wires such that you can otherwise terminate it. So there's that consideration. Conduit and cable tray fill calculations, and I don't think we will have enough time to get to those in any specific.